Hello and welcome to the second week of live problem solving session for the course Fundamentals of Semiconductor Devices by Professor Digvijay Nath. So, my name is Mayank Goel and I am a research scholar at the at IIT Department of Electrical Engineering, IIT Bombay. My research focus is on 2D materials and devices. So, details of this course. The instructor is Professor Digvijay Nath, who is a professor at ISC Bangalore. The plan for this week is like the study plan for this week is equilibrium electron hole concentration, temperature dependence of the concentration, charge neutrality, and incomplete ionization. So the tutorial sessions for my my tutorial sessions will be every Sunday 6 to 8 p.m. like today, and this is the Google Meet link where we meet. So like last week, I will be giving you some practice questions which which will help you understand this course a little bit more and you also help you in solving the assignments. And after the practice questions, you can ask me any doubts you have regarding the course. So first question, this is not an MCQ. What are the diagrams used to study band structures of semiconductors? If you know the answer, you can speak or type in the chat. There are different types of diagrams that we use to study band structures.
EK band diagram.
So, like tool generally that we use are EK diagram and a band diagram. I am telling you this so that you understand the difference between the both. So till now, in the last week, we were studying EK diagrams. So what EK diagrams are actually, they are energy versus the momentum vector K. So K is not K is not a real real value. It's in the reciprocal space, and the band diagram that we use is in the real space. So this is X value. So this is like literally the dimensions of our semiconductor. So like from point A to point B, it's the length of the semiconductor, and this value that we consider here is the band gap of the material that we find from the from the EK diagram. EK diagram is used to determine the band gap, which is defined as the highest filled valence orbital and the lowest unfilled conduct, conduction band orbital. So that gap that we use to determine our band gap, and that band gap is then used to determine the band gap across our semiconductor, like from point A to point B of our semiconductor. So till now our focus was on EK diagram. Now our focus will shift to band diagrams. So EK diagrams are used for solid state physics. That is, if we want to study the band structure, like how the bands are modifying and how this parabolic nature affects our mobility and effective mass, and how the transition optical transitions work between different from band to band transitions. But when we want to study the semiconductor as a whole, we come to band diagrams, and there we do our device physics, like if we want to study PN junctions or FETs, and Here we study the macroscopic changes like the doping effects or electric field effects. So that is the basic difference between these two diagrams. And now we'll, so till now our focus was EK diagram. Now we will focus on the band diagrams and how the band diagram gets changed by different purpose things. So like one of the methods is doping. So doping is described as adding impurities to a semiconductor, removing impurities from a semiconductor, heating a semiconductor, or cooling a semiconductor. So which of these is doping? Yes, the correct answer would be adding impurities to a semiconductor. Doping involves intentionally adding small amounts of specific impurities, which we call dopants, to a semiconductor material to alter its electrical properties. So by doping, we can increase the number of free charge carriers. So like last week we studied intrinsic semiconductors which have equal number of electrons and holes. So if we want to increase those charge carriers, we can make it either N type by adding donor impurities or P type by adding acceptor impurities. Now to continue this doping section, in the context of doping, what does N type semiconductor refer to? A semiconductor with more holes than electrons, a semiconductor with equal number of electrons and holes, a semiconductor with more electrons than holes, a semiconductor that is undoped.
A semiconductor with more electron than
More
hole.
than electrons.
It would be more holes than electrons. It is N type. So in N type, we you introduce donor impurities which provide extra electrons, which then go to the conduction band. So these extra electrons increase the conductivity of the material, and now we have more electrons and holes. So you can say that it is negative. There are more negatively charged particles than more positively charged particles. That is why it is called N type, negative type. Which element is commonly used for P type doping? Boron, silicon, phosphorus, gallium.
Boron.
The answer would be boron. Boron is often used to dope semiconductors like silicon to create P type material. Boron has one less valence electron than silicon, which so it takes an electron from silicon and it creates holes in the lattice, which are positively charged carriers, and this enhances the semiconductor's conductivity via hole movement. So in n-type doping, we were increasing electrons and electron movement was giving us higher conductivity. Now we are increasing holes and hole movement is giving us higher conductivity. What happens to the Fermi level when silicon is doped with phosphorus? It moves towards the valence band. It remains in the middle of the band gap. It shifts towards the conduction band. It becomes non-existent. So what will happen when we dope silicon with phosphorus? Yes, the answer would be it shifts towards the conduction band. So phosphorus is a donor impurity, so it's adding extra electrons to the silicon lattice. So this is increasing the concentration of charge carriers in the conduction band. So now we have more electrons in the more probability of charged electrons in the conduction band. So if we apply Fermi direct statistics, we can see that the Fermi level should be closer to the conduction band to fulfill our to fulfill the Fermi direct statistics. So when the Fermi level is moving closer to the conduction band and you calculate the probability of electrons in the conduction band, you will see that it now you have a higher electron concentration. So that is why we consider Fermi level to be shifting towards the conduction band. Now we will do some numericals. If the conduction band effective density of states, which is NC, is 2.8 into 10 per centimeter cube, and the valence band effective density of states, which is NV, is 1.04 into 10 per centimeter cube, and the band gap of silicon is taken as 1.1 eV, what would be the intrinsic carrier concentration at 300 Kelvin? So here you have to apply the formula for intrinsic carrier concentration, and you are given NC, NV, band gap, and temperature. I will give you some time to solve this. So anyone got the answer yet? Anyone with the answer? Nc is 2.8 into 10 power 19, Nv is 1.04 into 10 power 19, band gap is 1.1 eV, temperature is 300 K. No one has got the answer yet. It's been 5 minutes, so I'm continuing. So the answer would be 1 into 10 per 10 per centimeter cube. So you will have to use this formula, Ni equals to square root of NcNv times e raised to power minus Eg by 2 kBt. So if you calculate under root NcNv, you will get 1.71 into 10 raised to power 19. If you calculate the exponential term, you put band gap 1.1 to Kb. I am right here. It's written in the terms of electron volt per Kelvin. Usually, what you see is in terms of joules per Kelvin. This is in electron volts per Kelvin, and the temperature is 300. So the exponential term comes out to be 5.76 raised to the minus 10. So you multiply both of those, and it comes approximately 10 raised to power 10. It should be slightly less than like 9.8. So another question: if the intrinsic carrier concentration decreases exponentially with increasing bandgap energy, which of the following materials will have the lowest intrinsic carrier concentration at room temperature? Silicon with bandgap 1.1 eV, gallium arsenide with bandgap 1.43 eV, germanium with bandgap 0.66 eV, gallium nitride with bandgap 3.4 eV. This is very simple question. Anyone can answer this question? Please talk or write. This is an interactive session. So the answer to this will be gallium nitride. Use this same equation. So you are given that when you increase the band gap energy, your intrinsic carrier concentration is decreasing. So by you don't even you have to look at this formula since it's already given in the question, the relation. And so by logic, gallium nitride has the highest band gap, so it will have the lowest intrinsic carrier concentration. This is also a numerical question. A semiconductor has a band gap of 2.5 electron volts. If the intrinsic carrier concentration at 300 Kelvin is given as 10 per 6 per centimeter cube, Estimate the intrinsic error concentration at 340 Kelvin. Assume that the density of states remains constant. Is anyone trying to solve this question? For band gap 2.5 electron volts, you are given that the concentration at 300 Kelvin is 10 power 6. Now you have to calculate the carrier concentration at 340 Kelvin. 10 raised to power 7 per centimeter cube, 2.5 into 10 raised to power 6 per centimeter cube, 3 into 10 raised to power 8 per centimeter cube, 3.5 into 10 raised to power 6 per centimeter cube. Which would be the correct answer? Anyone has got the answer? So the answer for this would be 3 into 10 raised to power 8 per centimeter cube. And it is given by the same formula. If you don't you just need the temperature variation, the rest of the things are same. And that that comes out to be 3.4 into 10 minus 3. So by change of variables you will get x into is equal to 3 into 10 raised to power 8 per centimeter cube. So next question, which of the following best represents the donor ionization process in an n-type semiconductor? Electron transitions from conduction band to valence band, electron moving from donor level to conduction band, hole moving from valence band to acceptor level, electron recombining with the hole. The answer would be electron moving from donor level to conduction band. So so when you have an n-type semiconductor, the doping when you dope it, it introduces donor levels just below the conduction band. So that is how the Fermi level is increasing. So when you ionize these donors, so the electron moves from the donor level and jumps to the conduction band, and it leaves behind a positively charged donor ion. So due to this ionization, donor ionization, the number of free electrons in the conduction band are increasing, and this is how it's called. It's the called n-type semiconductor. So next question: which equation describes the relationship between the number of electrons in a semiconductor and the effective density of states? N equals to Nc e power Ef minus Ec by Kt. P equals to Nv e power Ev minus Ef. E power Ev minus Ef by Kt. Np equals to Ni square, or all of the above. So the correct answer would be all of the above. So this equations give us the and the carrier concentration for the n-type semiconductor for elect free electron carrier concentration. This gives us the free hole carrier concentration, and this relation is the electron carrier concentration times hole carrier concentration will be the square of intrinsic carrier concentration. Next question. The condition for applying the Boltzmann approximation to the carrier concentration equations is absolute modulus of mod EF minus EC is greater than 3 kT, mod EF minus EC is less than 3 kT, mod EC minus EV is greater than 3 kT, mod EF minus EV is greater than 3 kT. So the answer for this would be both A and D. So Boltzmann approximation assumes that the current distribution is following the classic Maxwell-Boltzmann statistics, which is only valid when the Fermi level is not too close to the conduction band or valence band. So, so this gives us the condition for conduction band, and this gives us the condition for valence band. So only when the distance is greater than 3 kT, we can apply the Boltzmann approximation, which is the formula we had just seen. So these formulas come from Boltzmann Maxwell statistics. They can only be applied when it is greater than 3 kT. If it is less than 3 kT, we call them highly doped semiconductors. We'll study more about them later. Another numerical. If the intrinsic carrier concentration Ni in silicon at 300 K is 1.5 into 10 raised to power 10 per centimeter cube, what is the carrier electron concentration in a silicon sample doped with 10 raised to power 16 per centimeter cube donor atoms? Is it 10 raised to power 16 per centimeter cube, 1.5 into 10 raised to power 10 per centimeter cube, 10 raised to power 14 per centimeter cube, 1.5 into 10 raised to power 8 per centimeter cube? So you have to use the formula you had just seen 2 questions back. Actually, in this question, you don't have to use any formulas because you are giving that uh, doping is 10 raised to power 16 per centimeter cube donor atoms. So, so since it's donor atoms, so they will create an n-type semiconductor. So it will increase the electron concentration, which will be equal to the donor concentration, doping concentration, which is 10 raised to power 16 per centimeter cube. Now, to make it a little complicated, we can ask what is the whole concentration. If the intrinsic carrier concentration in silicon at 300 Kelvin is 1.5 into 10 by 10 per centimeter cube, what is the whole concentration doped with 10 to the power 16 per centimeter cube donor atoms? 1.5 into 10 to the power 4 per centimeter cube, 3 into 10 to the power 5 per centimeter cube, 2.25 into 10 to the power 4 per centimeter cube, 1.5 into 10 to the power 6 per centimeter cube. Anyone can answer this question? It is very simple. You are given intrinsic carrier concentration 1.1 10 per centimeter cube. You have been given donor concentration 10 raised to power 16 per centimeter cube. You have to calculate the whole concentration.
D.
The answer would actually be C. So we just studied that Np equals to Ni square. So since our electron concentration would be 10 raised to power 16, so we can use this formula and we will get that your whole concentration is 2.25 into 10 raised to power 4 per centimeter cube. This is another numerical. Given that the conduction band density of states Nc is 3 into 10 raised to power 19 per centimeter cube, and we have an n-type doping concentration Nd, which is 10 raised to power 17 per centimeter cube, find the position of Fermi level relative to the conduction band at 300 Kelvin. 0.15 electron volts below conduction band is 0.2 electron volts below conduction band, 0.25 electron volts below conduction band, 0.3 electron volts below conduction band. So you have conduction band density of states, you have doping concentration, and you have temperature, which are enough to solve this problem. So the answer to this would be, anyone has got the answer yet? So the answer for this would be 0.15 electron volts below AC. So we just read that, we just got the formula that electron concentration is Nc e raised to power EF minus EC by KT. So if we rearrange that, we can get EF minus EC is minus KT log of Nc by Nd. And when you put the, so for 300 Kelvin, KT is given as 26 milli electron volts, and Nc by Nd would be 300. You can see 3 into 10 to the power 19 divided by 10 to the power 17. And when you solve this, you will get 0.15, and since it's minus, so it will be below EC. If the Fermi level has a slope, what does it imply? The material is in equilibrium, there is a current flow, the band gap is changing, the doping concentration is uniform. Anyone can solve this question? So the answer to this would be that there is a current flow. So if the Fermi level has a slope, that would mean that there is a difference between the Fermi level going from left to right, which 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 can only happen when the material is not in an equilibrium, because because there is a movement of charge carriers due to an applied electric field, which is causing a gradient in the Fermi level, and when this is happening, there would be a current flow. What is the term used when the free carrier concentration decreases due to the lowering of temperature? Carrier freeze out, charge neutrality, doping effect, thermal equilibrium. What is the term used when the free carrier concentration decreases due to lowering of temperature? So the answer to this is carrier freeze out. So so we know that so we know that with when you when you decrease the temperature, so your we know that we just read that the carrier concentration is given by ionization of dopants from donor level to conduction band, or in case of p-type semiconductors, ionization of dopants will be from valence band to acceptor levels, which are just above the valence band. So when you go to very low temperatures, there will not be enough thermal energy to to overcome the ionization energy and give us free carriers. So the concentration of free carriers will decrease, and this term is called carrier freeze out. Next question: in an extrinsic semiconductor at moderate doping levels, the majority carrier concentration is approximately equal to the intrinsic carrier concentration, the donor or acceptor doping concentration, the square of the intrinsic carrier concentration, or zero. Anyone able to answer this question? The answer would be B, donor or acceptor doping concentration. So at, at, at in extrinsic region, the we consider that all the dopants are ionized. So the carrier concentration would be is considered equal to the donor or acceptor doping concentration. A high temperature region in a doped semiconductor where the carrier concentration is dominated by thermally generated carriers is called extrinsic region, freeze out region, intrinsic region, or ionization region. Anyone can solve this question? The answer to this would be intrinsic region. So we have we have seen the formula that intrinsic carrier concentration uh, increases exponentially with temperature. So you can see the so if we go to very high temperatures, our all the all the all the electrons in the valence band get excited to the conduction band, and the the all the carriers are now my intrinsic carriers. So my dopant concentration is now is now my intrinsic carrier concentration has dominated over my dopant concentration. So all the carrier dynamics are now being controlled by the intrinsic carrier concentration itself and not the dopant concentration. Hence, it is called intrinsic region. So my semiconductor is behaving like an intrinsic semiconductor even though it is doped. The extrinsic region in the temperature versus carrier concentration graph is characterized by dominance of intrinsic carriers, constant carrier concentration determined by doping, rapid increase in carrier concentration with temperature, complete depletion of free carriers. So the answer to this would be constant carrier concentration that is determined by doping. So, so over the whole extrinsic region, I will have a constant carrier concentration, which will be given by my dopant concentration. If we go higher than this region, we get an dominance of intrinsic carriers, which is caused by a rapid increase in carrier concentrated temperature, and we just studied that it's called the intrinsic region. If we lower the temperature, we will deplete the free carriers because of carrier freeze out. And if we go even below, we will have a complete depletion of free carriers. So, what condition must be satisfied in semiconductor physics regarding charge? Positive charges must exceed negative charges. Total charge must equal zero. Negative charges must exceed positive charges, or charge can vary. It doesn't matter. The answer to this would be total charge must equal zero. So, if your charge is not equal to zero, you will have movement of carriers inside the semiconductor till your it will try to e- equalize the charges across the semiconductor. So you will have movement of carriers, and eventually they will become zero. Since if you see, added any you have not added any charge to your semiconductor during doping, you have only added atoms. So you have not added charge from anywhere, so your total charge must equal zero. If it is not equal to zero, your carriers will move across the semiconductor such that your total charge equals zero. And this is called charge neutrality. When both p-type and n-type and p-type doping are present, how is the charge neutrality condition expressed? P plus Na equals to n plus Nd, P plus Nd equals to n plus Na, P plus Nd plus Na equals to n, P plus Nd plus Na equals to n plus Ni. So the answer to this would be P plus Na equals to n plus Nd. So your Na is your acceptor concentration that you have added. Your doped acceptor p-type concentration. Nd is your doped donor concentration. P is your free hole concentration, and N is your free electron concentration. So your P so now I want my total charge to be zero. So that is given by the equation P minus N equals to Nd minus Na, and you can rearrange that to say P plus Na equals to N plus Nd. When the Fermi level approaches or exceeds the conduction band due to high doping, the material is referred to as an intrinsic semiconductor, a degenerate semiconductor, a lightly doped semiconductor, an insulating semiconductor. Yes, the answer to this would be a degenerate semiconductor. So this is when you cross the 3 kT limit and your Boltzmann statistics are no longer valid. So you go to a different kind of statistics, and since your le, le, Fermi level is almost near the valence or conduction band, almost conduction, so it is acting like it is part of the conduction band, and we know that inside the conduction band the statistics followed are Fermi direct statistics. So your Fermi level is following the similar statistics and not the Boltzmann statistic that it would generally follow. And in this sense, it is considered it is called a degenerate semiconductor, where it starts following the exponential Boltzmann statistics. The effect of band gap narrowing in highly doped semiconductors occurs due to the increase intrinsic carrier concentration, lattice distortion caused by excess dopant atoms, an increase in phonon scattering, or the suppression of minority carriers. So the answer to this would be lattice distortion caused by excess dopant atoms. So when you are doping it at high levels, the lat so your dopant atoms are sitting at your lattice positions. That is how they are able to contribute to your st- semiconductor physics. So when you have a very high excess amount of dopants, so they create a distortion in your lattice, and this distortion will change your lattice constants, your band structure, etc. And that is why your band gap narrows down. So last question, very simple numerical. A semiconductor is doped with 10 raised to power 18 centimeter cube donors, but only 90% of them are ionized at 300 Kelvin. What is the actual free electron concentration? 9 is to 10 to the power 17 per centimeter cube, 10 is to the power 18 per centimeter cube, 10 is to the power 17 per centimeter cube, 5 into 10 is to the power 16 per centimeter cube. So till now we were assuming that uh, my free carrier electron concentration is equal to my donor concentration, but there is something called incomplete ionization where not all the donors will get ionized at my particular temperature. So here we are assuming that only 90% are ionized. So what will be my electron concentration? Free electron concentration. This is a very simple question. So the answer to this would be 9 into 10 to the power 17 per centimeter cube. It is very simple. You just have to do 90% of 10 to the power 18, which is 9 into 10 to the power 17 per centimeter cube. And that is the questions I had for today. Thank you for your attention, listening to me. Now, if you have any doubts, you can ask. Anyone has any doubts?
No, sir.
Yes. You have any doubts?
No, sir.
Yes, speak.
Okay, welcome back. So we ended the last lecture with this promise that today we shall start mobility. Okay, we should not forget what we have learned till now about doping and carrier concentration and how to
Okay, sir. Thank you, sir.
Yes.
Thank you, sir.
Do you have any doubts?
Not now, sir.
Okay.
to calculate carrier distributions and so on. We'll go ahead and study mobility today. And once the word mobility basically means that we are now in the discussion of low field transport in a way. So what is this low field transport, high field transport? Okay, those are two things we have to
Yes. Do you have any doubts?